Now let's see how can we compute probabilities with this exponential function. First of all, the exponential function that we have is f of x equal to a constant, multiplied by e to the minus mu minus x divided by c. We know that the constant a is responsible for the height, and constant c is responsible for how is the shape of the bell. Now, to find out a or c, we have the following equations. First of all, the integral of our density function, probability density function, is equal to 1. Second, the integral from minus infinity to infinity of x minus infinity to infinity of x multiplied by f of x dx must be equal to mu. That one we can be sure because the function is symmetric, so that's mu. And the last one is the definition of the variance. So the integral from minus infinity to infinity of x minus mu squared multiplied by f of x dx is equal to the variance. So if we consider these two equations, we can solve for constants a and c, and we can have the final form of the Gauss or normal distribution. So we have that f of x is equal to, let me write it in red, 1 divided by the square root of 2 pi sigma squared multiplied by e to the minus x minus mu squared divided by 2 sigma squared. So our constants a and c are represented by these two numbers. Now, how do we use this to compute probabilities? That's the usual way that we do with a probability density function. So we have our PDF, and we have that the probability of x being less than a given value, is equal to the integral from minus infinity to a of f of x dx. So if a is, for example, in this point, so that will represent this integral. Now, the probability of x being bigger than b is equal to the integral from b to infinity of f of x dx, and let's say that b is in this point, so that will represent this area. And finally, the probability of x in between a and b, it will be represented, it will be the integral from a to b of f of x dx, and that will be this area over here. Remember that when we have a continuous variable, we cannot say the probability of x being equal to something. We have to always have a range. The probability of x equal to a is 0 because the area is going to be 0. Okay, now I'm going to invite you to visit this page in which I prepare a little demonstration of the Gaussian function and how to compute the probabilities. Desmos has built in the normal distribution function. We can observe here the function is called normal dist with parameters mean and standard deviation. And here is the plot of the function. In this case, the mean is 0, so it is centered at 0. And the standard deviation b for this particular case is 0.5. So it will be a measure of how thin or thick is the bell. So if I increase the standard deviation, it will be fatter and fatter and fatter. Like, look, standard deviation of 1.3 is very flattened bell. If I go in the opposite direction, smaller standard deviation, it will start to be skinnier and skinnier. So it is a measure how thick is the bell. And there is another interesting thing about the function in Desmos. We can compute the cumulative probability, and that means computing the integrals. So let's have an example. Let's say we are going to compute the integral from -infinity to 0. In this case, we are computing half of the area, and that's exactly what we expect. Half of the area, 0.5. So if we compute to infinity, to a larger value, like 40, for example, it's already 1. So in infinity, it will be 1. We can choose any two values, and I will show you in the next slide. Well, in the next example. Okay, so let's select a different one. So the mean in this case is 3, and the standard deviation is 5. I'm going to compute the integral in between 3 and -a. So if I put a, for example, equal to 0, so that should be equal to 0. So I'm computing the integral from 3 to 3, so that's 0. So let's increase a to value of 0.5. So I'm moving 0.5 in this direction and 0.5 in this direction. So that's actually the standard deviation, 0.5. And the probability of being in this region, we can see, is 0.6826. So the meaning of having, this is mu minus sigma, and mu plus sigma, we are covering 68% of the probability. So if we keep increasing to 1, so in this case we have double the standard deviation, and the probability is 0.95. So the probability of being in -2 standard deviations to the left and 2 standard deviations to the right is 95%. And so forth, if we keep going, 1.5, so that would be 1.5 standard deviation. We are almost covering the whole domain. So that gives us an idea of the standard deviation comparison with the amount of region that we cover when we integrate. So to keep in mind, to have one standard deviation to the left and one standard deviation to the right, we cover 68% of the total probability.